students, I welcome you all for another lecture on the course Computer Architecture and Organization. In last few classes, we are discussing about input-output organization. In that, we discussed different concepts like I/O techniques, that is programmed I/O, interrupt-driven I/O, direct memory access. Later, we discussed about different bus protocols, that is a synchronous bus as well as asynchronous bus. In today's class, we are going to discuss about another important topic, that is interface circuits. In this, what we are going to learn is what is the use of an interface circuit and what are the different types of ports we have and how we are connecting an I/O devices to the computer system with the help of this interface circuits. All these things we are going to discuss. Right. We straight away enters into the concept trees. So what are interfaces? I/O interface consists of the circuitry required to connect an I/O device to the computer bus. What this is? Definitely we need some interfacing circuit to connect an I/O devices to the computer system. What is the reason for this? We know that we have a different I/O devices, their speeds are different, their logics are different. So that's why we are not directly connected our I/O devices to the computer systems right away. These I/O devices we can call as external devices as well as peripherals. We know that. So you can assume this is your computer system. In that, this is a system bus. This end you have a CPU and this is a memory, and you can assume this is our I/O interface. This I/O interface we can also call as I/O module. So this is an I/O module. It is connected to this bus like this, and this is our CPU. So it is connected to the bus like this, and this is a memory. Again, it is also connected to this bus. This bus generally we can call as system bus or a computer bus. So this end you have I/O devices or an external devices. Let I am assuming these are my external device. This is external device 1 and this is external device n. These devices are connected to our computer system with the help of this I/O module. So here that what I am saying. So I/O interface consists of this I/O module consists of a circuitry that is required to connect these I/O devices or external devices to the computer bus or system bus. That's the meaning of this. Next, one side of interface which connects to the computer bus, that is nothing but the system bus. This end of our I/O interface or I/O module was connected to the system bus, that is called a computer bus, and other end it is connected to the external devices or I/O devices. So that is the meaning of a second point. Coming to the next, the end which we are used for connection of I/O devices. This end or this side, what we can call is port. This is what we can call is port. So the I/O device side of the interface is called as a port. So this end we can call as port. Here this port we have different types. So these types of ports are purely depends on the type of I/O devices we are connected to our I/O module. So basically your I/O devices are two types. One type of devices we can call as parallel devices. That means the devices which can accept or transfers multiple bits at a time. That means, for example, your external device is an input device. That input device transfers parallelly some n number of bits to I/O interface at a time. Or your device is an output device. Then the device receives multiple bits simultaneously from an I/O interface. So such devices what we can call is parallel I/O devices. So to connect the parallel I/O devices to your I/O interface, that I/O interface must have parallel port. So one variety of I/O port is parallel port. This is the first thing. And the second variety of port is nothing but a serial port. What is this serial port? Like your parallel devices, we have another variety of I/O devices are the serial I/O devices. That means the I/O device either it can transfer or it can receive bit by bit. In order to connect such type of devices to our I/O interface, definitely we took the help of serial port. So there are two port types of ports. One is parallel port and second type is serial port. So there are two varieties of ports. Next, the parallel port transfers data in the form of a number of bits. Normally, it is either 8 or 16, 2 are from the device. Let me assume this is my I/O interface. This is I/O interface or an I/O module, and here I have an external device or I/O device, which is a parallel device. That means this device either it can transfer parallelly a number of bits or it can receive parallelly a number of bits. That means here, for example, I have this n number of lines are exist between this interface and this interface. So here this is line 1 and this is line n. Total I have n lines. So this I/O device may transfer n number of bits at a time to this I/O interface, or this I/O device receives n number of bits from I/O interface by using n lines. So then this particular port what we can call is parallel port. Parallel port. Why? Because an I/O device can transfer or receive multiple bits at a time. So definitely here we are using parallel port. So that's why here what we are saying is the parallel port transfers data in the form of a number of bits. Normally here this n is either 8 or it may be 16. 2 are from the device. That's the meaning of this. And second one is the serial port transfers and receives data 1 bit at a time. So let me assume this is my I/O module or an I/O interface, and here I have an I/O device. This I/O module or I/O interface receives or transfers data to this I/O device with the help of only one communication link. So once we have only one communication link is exist for data transfer between an I/O module and I/O interface, at this end you have a port. That port what we can call is serial port. So what a serial port can do for us? The serial port either transfers or receive 1 bit at a time, 2 are from I/O device. That's the meaning of this. And here important thing is the conversion from the parallel to serial and vice versa takes place inside of the interface circuit. So the meaning of this one is this interface circuit can do the conversion of data from parallel to serial or serial to parallel. Why? Because other end to this interface in circuit is we have a computer bus or a system bus. No doubt the communication is going on, this system bus is always in parallel. That means in this end you have a CPU as well as a memory. This CPU and memory can communicate in parallel with the help of this bus. So that whenever your CPU want to communicating with an I/O device, the device knows only parallel communication, then it will transfer data parallel to this system bus. From the system bus it is a transfer to I/O interface, later that is a transfer to the device. Here there is no need of conversion because our CPU sends data in parallel and your device also receives data in parallel. In this case there is no problem. But coming to this, here we have a device. The device only receives data in serial form, that means bit by bit, or this device may transfer data to I/O interface again bit by bit. The other end of this I/O interface is we have a system bus. In this system bus again we have a CPU was connected as well as memory elements are connected like this. No doubt this CPU or a memory can communicating with this I/O module only in parallel. But this time you have an I/O device only knows a serial communication. Whenever the CPU want to communicating with this device, the CPU transfer data to this I/O module in parallel form. But this device can't send parallelly the information to this I/O device. Why? Because this I/O device only knows a serial communication. So here what I need is this I/O module or I/O interface must be able to convert the received data which is in parallel to serial form in a similar way. For example, this device was an input device. It transfers the data to I/O module only bit by bit. But other end of I/O module is parallel communicated devices. So this I/O module again what it has to do is it can do a reverse process what it done previously. Previously what it do, it will convert a parallel data into serial form. But now this I/O module what it has to do is it will convert a serially received data into parallel form. That's why your I/O module must have a conversion from parallel to serial as well as vice versa. The required circuit what is necessary to do this conversion that is exist in this I/O module. That is the meaning of this. And next point is the parallel port uses multiple pin connector between the device and the processor. Absolutely. So this is your parallel port connector device. So this here we need a connector. This is your connector. That connector has multiple pins. With the help of these multiple pins, your I/O device can communicating with the CPU with the help of I/O interface. So here this whole thing what we can call is a connector. The connector have a multiple pins so that here the parallel port uses multiple pin connector between the device and the processor. That is the meaning of this. A cable with as many wires as the number of bits transferred simultaneously, hence it is suitable for the devices that are physically close to the computer system. Absolutely it is true. So here important thing is where we prefer this parallel connectors or the connectors which have multiple lines. The simple solution is or the simple answer is the devices which are closer to the processor or the devices which are close to the computer system. If I want to connect such type of devices, no doubt I can go and use a parallel connector. That means I have to go and use a parallel port. So parallel port uses parallel connector. With the help of that, your processor can communicate with I/O devices in parallel. So that is the meaning of this. Coming to serial port uses a single pin connector between the device and the processor. Hence, it is useful for the devices that are at a longer distance. Absolutely. So once the distance between your computer system and a device is very far, in that case I didn't go and use generally a parallel ports or multiple connectors or parallel connectors. Why? Because if I use parallel connections between a computer system and that device, the making cost of the system is increases because you have to go and incorporate multiple lines between that device and your computer system. It is a costly affair. So that's why in the particular occasion what we prefer is we prefer a serial port and a serial or single pin connector. So generally multiple connector where we are using is the distance between the device and your computer system is very less. There I can go and use multiple pin connector. There definitely I use parallel port for the connection of devices. Similarly, where I use a single pin connector is the distance between the device and the computer system is very far, or the distance between a computer system and the device is too longer. That time I can go and use single pin connector. There absolutely I can go and use single serial port interface. That's no doubt. That's the meaning of this. So let first we discuss about what a parallel port. How we are connecting our devices, the devices which knows a parallel communication to the computer system with the help of parallel port, with the help of an I/O interface which have parallel. That we can go and discuss. In that process, in this example, I am going to connect a keyboard which is one of the input device to my processor with the help of I/O interface, which is here input interface. So which shows a parallel communication. It means it has a parallel port internally. So that we are going to discuss. Coming to this. Here my assumption is, what are the processor here I have? This processor is a 32-bit processor. This is the first thing you have to remember. That means this processor have 32 data links. This processor can communicating with the external devices with the help of 32 data links. And one more thing, this processor can process 32 bits at a time. That means the word length of this processor is 32 bits. That you remember. That is the first thing. And my second assumption is, this processor addresses these I/O devices by using an addressing scheme that is called memory mapped I/O. So here my processor address this I/O device with the help of a scheme which is memory mapped I/O. So just you recollect guys, there are two types of addressing schemes to address I/O devices in our computer system. One is a memory mapped I/O and second one is I/O mapped I/O. What is the important thing regarding to memory mapped I/O? The important thing regarding to this memory mapped I/O is, from a processor point of view, it treats each and every I/O device like a memory location. If it treats each and every I/O device like a memory location, no doubt your processor can't go and use a separate instructions to communicating with the memory. It didn't go and use a separate control signals to communicating with the I/O devices. Because whatever the control signals our processor can use to communicating with the memory, and whatever the instructions your processor can go and use to communicating with the memory, the same type of instructions and same type of control signals it will use to communicating with I/O devices also. So designing of a system is very simple. So here my second assumption is, our processor can address an I/O device with the help of memory mapped I/O. That is the second assumption. Coming to the third assumption, here I am going to use asynchronous bus protocol. Asynchronous bus protocol. So in that case, I use two control signals in communication between an initiator and a target. One is master ready as well as second one is slave ready. With the help of this, my communication is going on between an initiator as well as target. So these are three important assumptions here I consider. The first one is, my processor is a 32-bit processor, that is number one. And number two, my processor can address I/O device with the help of memory mapped I/O. And the third thing is, here I can go and use asynchronous bus protocol. It means in the communication I use two handshaking signals. One is master ready and second one is slave ready signals. So we can go on and explain this concept. Here my aim is, I am going to connect a keyboard to a processor with the help of an interface. See here friends, up to this part, this whole thing we consider as keyboard. This whole thing we consider as keyboard. So we know that the keyboard consists of different keys which are arranged in a particular order. We know that. So this is a keyboard which consists of a number of switches. Generally, if you remember a keyboard, if you press any key over a keyboard, no doubt it internally generates a 7-bit ASCII code. That's why generally keyboards we can call as ASCII keyboards. So here important thing is, if I press any key over this keyboard, the corresponding pressed switch ASCII code was transferred to an encoder. This encoder converts whatever the information it receives from this keyboard switches. Equivalent ASCII code was transferred to our input interface with the help of this data lines. So listen carefully friends. Here I press some switch or a key on my keyboard. No doubt automatically it will generate certain signals. Those are given to an encoder. Now the encoder generates an ASCII equivalent code for a pressed switch or a pressed key that is given to the input of this data in. But here one more important thing is going on here, friends. That is, here it is not only an encoder, it is a combination of an encoder and debouncing circuit. So what is the use of this debouncing circuit? These debouncing circuits suppress the bounces what we are getting from a pressed key. That means we are getting some bouncing conditions that we are getting from a pressed key on this keyboard that can be suppressed with the help of this debouncing circuit. So this encoder not only generates ASCII equivalent code for pressed key, as well as it debounces or it suppresses the bounces what we are getting from pressed key. There are two things that are happening here. So once a key was pressed, then it will transfer that information to this input interface with the help of these lines. At the same time, here one more important thing that was going on, it will generate a value signal. So we can go and discuss this in general. See here, friends, this is our input interface. This interfacing circuit have a data in register, which is generally an input buffer register, and this buffer register status can be provided by a status flag that was SIN. So these are two exist in this. Coming to the processor end, what we are connecting? Generally in a processor end, that means the connection from other side of your I/O interface was connected to the system bus. In a system bus, we have an address bus, data bus, and remaining all these things are considered as the control signals. Generally here this is R/W bar is considered as read/write bar, and this is as usually master ready, and this is a slave ready. Right. Now we can go and discuss somewhat clear about this. So if my processor want to take something from an input device, first what my processor can do is it will generate an address of that corresponding device. The generated address it will transfer to the device with the help of address bus. So it places first the generated address on the address bus. Let me assume that was the first operation. At the same time, after generating an address, what my processor can do is, on that selected device, my processor going to do either read or write operation. Here my connected device was a keyboard, which is an input device. No doubt, my processor always receives something from this keyboard. So that the processor generates a control signal that is a read over this R/W bar signal as a second operation. That you can assume. This is a read. Once it activates these two, later what it do is, it will inform that information to this particular input interface by activation of master ready as a third operation. Once it receives the master ready, that indicates that our processor is ready to participating in data transfer. Then what my input interface can do is, it receives an address from an address bus, it decodes that address, it will identify that address was connected, belongs to the connected device, and later it will receive the control signal. It will identify that which operation our processor wants from the selected device. So here what this input interface can identify is the generated address belongs to keyboard, and your processor wants some information from that keyboard. That's why it will generate a read signal. Then what it do is, it will go and gather that information from this. So once if I press any key over this keyboard switches, no doubt its corresponding information was transferred to an encoder and key debouncing circuit. It will generate equivalent ASCII code for pressed key, as well as it suppress the bounces what we are getting from the pressed key or pressed switch. That's important. So that is a transfer to your input interface with the help of these data lines. So that means here I use this type of notation that indicates this notation represents multiple bits are transferred between the input device and this input interface. So that you can imagine what is a connector we use between this interface and this input device. It is I think you identified, guys. So here we use definitely a multi-pin connector. Multi-pin connector, because here I am transferring n bits. multiple connector between this. That means here I have a parallel port. So it received data from this encoder and debouncing circuit, was copied into this data in register as an operation number 4. At the same time, operation number 5, it will activate a valid signal. It will activate a valid signal that indicates the information what it transferred by this encoder and debouncing circuit, which is a valid data, so it can be copied onto data in register. At that incident, this SN is set to 1. This is the 5th operation. Once it SN is set to 1 and data in register is filled with the data, then your input interface activates this slave ready signal as a 6th operation. So once your processor receives this slave ready signal, that indicates that our I/O interface or input interface already gathered the data from the input device. It was there on this data in register. So that's why SN is set to 1. Now I can go and collect the data from this input interface. So collection of data from this input interface with the help of data lines, that was happened as a 7th operation. Like this, the communication was going on between a processor and this keyboard with the help of an input interface. I hope you understand this. Now, we are going to discuss about the internal circuitry of this input interface, how it looks like to do all these operations. See guys, this is the internal circuitry of your input interface. It consists of different logic gates, it consists of different tri-state buffers. All these things, address decoder, everything all exist. So we can go and analyze what this circuit is. So whenever my processor want to communicating with any device, first of all what it do, it will generate an address. The processor generate an address with the help of an address lines. It will generate an address of a device with the help of address lines. I have a 32 address lines, that is from A0 to A31, but out of 32 address lines, I use only 31 address lines to select my device. So that's why I give that address information to my address decoder. The address decoder generates only one address. It will generate or it generates only one output, which is a valid output. For example, this is 1, you can assume. So I put some address here. According to that, it will output is set to 1. This bit goes to the input of this AND gate here, as well as this AND gate here. Right now, here this A0 decides. Either our processor collects the data from the device with the help of this tri-state buffers, which are already stored in this data in register, or it will go on to access the status flag, that is SN information, from this I/O interface that is decided by A0. For example, I would like to receive only a data information. So I make this A0 is equal to 1. If A0 is equal to 1, output of inverter is 0. This goes to the input of this. But coming to this particular one, it is 1. Right now, another two inputs for these two AND gates is, one is a control signal, read/write bar, and second one is master ready. That means your processor is ready. Whenever your processor want to go and take a data from any external device, no doubt it always generates master ready, so that it is act to high signal. So it is absolutely 1. So this is 1 and this is 1. And coming to one more input is left for this AND gates, that is a read/write bar. Here our aim is read the data from an input device, so that here this signal is again logic 1, because there is no bar over R. That represents R represents read and it is up to high signal. So this is 1, so this bit is 1 and this bit is 1. So now we can go and observe guys the inputs of both AND gates. Like you can assume this is gate 1 and this is gate 2. Gate 1 output is 0 because one of the input of AND gate is 0. So at least one of the input of AND gate is 0, no doubt in respect of remaining inputs, AND gate produces logic 0 at its output. But coming to gate 2, all the inputs of AND gate is equal to 1, so that it will produce as logic 1. Once it produces logic 1, it goes to it is used as an enable signal for these are tri-state buffers or drivers. Once this enable signal is 1, whatever the data that was present here and here, that is a transfer to your data lines D0 to D7. That means the data which is from this data in register was placed onto data lines only when this enable bit of this particular drivers or tri-state buffers are enabled, or those tri-state buffers are set to 1. The tri-state buffers are enabled or they are activated with the help of this enable signal. Then and only what was present at input of those buffers or drivers, that is simply transferred to output end. So in this fashion, my processor collects the data from input interface by activation of these signals. Let you can assume I am going to read a status information, then all the signals information is same except only one, that was A0. I am already told you that A0 is equal to 1. I go on to collect the data from IO interface. If it is equal to 0, I can go and access the status information, that was SIN, which was present in status flag. So I change only this A0. So if A0 value is 0, it is 0. The output of this particular inverter is changes to 1. It is changes to 1. And this inverter value is directly connected here, it becomes 0. So that output of AND gate 2 changes to 0. And output of AND gate 1, here it is 1. Output is 1. If it is 1, what happens? It is again going to use it as enable signal for this driver or a tri-state buffer. What is the input for this? The input for this is the status flag, which is SIN. If SIN is set to 1 here, the same thing is received by your processor with the help of data lines D0. So, if A0 is equal to 1, your processor collects the data from our input interface or IO interface. If it is equal to 0, our processor receives only status information from it. So, I am already clearly told you guys, that is, whenever an external device transfer a valid data to input interface. So see guys, previous slide, that is here. Yes. So whenever this particular input device transferred a valid data to data in register, that incident I told you that this valid signal was active. Valid signal is equal to 1. So if you remember that concept, whenever this valid signal is 1, that means here we are getting a valid data from an input device that was copied onto this data in register only when this valid signal is set to 1. Because this valid signal is act as clock signal or enable signal for this particular one. So that instant what is the present here that was stored onto this particular register. At the same time that is goes to make your SIN is equal to 1. That means your status flag is set to 1. So here important thing is, if valid signal is 1, no doubt our input device transfer a data into our input interface. The data was copied onto data in register only with the help of valid signal. At the same time the valid signal may set to 1, that is SIN value is set to 1, that is your status flag. So like this your interface circuit consists all these things. I hope you understand how we are connecting a keyboard to your processor with the help of an input interface. In a similar way, if I want to connect an output device, for example, here my output device was a printer. Again, my assumption was my processor is a 32-bit processor, and it used memory mapped IO to address this printer, and it used asynchronous bus protocol for effective communication between a processor and that device with the help of this output interface. So for that case I use a master ready as well as slave ready signal. Again, here the scenario was same. If my processor go and transfer something to a printer, first it will generate an address, and second thing it will place a data over the data lines, and it will activate write control signal, and it will activate master ready signal. By activation of all these things, this output interface interface gather data from a processor, which is a transfer over the data lines that was copied onto this data out register. Once the data out register is filled with the data, this SOut is set to 1. That indicates that data out register is filled with the data. Then it will place the data onto the data as a fifth operation. Then it will inform that information to printer by sending off valid signal. Once it receives a valid signal, then printer collects the data over these lines. Once it receives the data, it will print it, and it is ready to receive one more data. What it do is, it will go back idle signal as a seventh one. Once it will send back idle signal, that means your SOut makes to 0. Once SOut makes to 0, what's the meaning of that? Already data what is there on this data out register in this output buffer, I already received that and I printed, and now this data out register was empty. That information is given to this output interface. Later your output interface transferred a slave ready signal. That means again this is ready to accept whatever the data again you are sending to me. Like this, the data was transferred from a processor to the printer with the help of this output interface. Again, we can go and see the internal diagram of this. This is an internal diagram of that. Again, operation is same. Here our data out register and two AND gates and this address decoder. Our previous case, what we are doing on a previous case, the same thing here we are following. Again, here first we place an address over these lines. And here also our condition is a not signal decides either data was transferred to data out register, or I can go and gather the status information. So that is again same to the previous case. So this A1 to A31 selects a device address, and A0 decides either our processor transfer a data or it will go and collect a status from it. That is decided by signal A0. So you can go and verify this. So output of address decoder is always 1. So this is 1 and this is 1. And next thing is here my operation was if I transfer the data, that means I am going to write. So I am going to write, here I place a data, the data was copied onto this, and that is to transfer to output only when this is at 2. So if I do a write, this signal is 0. If it is 0, so this is 0. Output of inverter makes 1. So I can find out what is the output of gate 1 and gate 2. So gate 1 I can straight away found. It's one of the input of AND gate is 1, so that no doubt output is 0. Now I can go and verify the remaining two inputs for AND gate 2 decides what's the output value is. The remaining two input for this, one is a master ready, it is always makes 1. So this is 1. And second thing is next input was A0. If A0 is 1, I am going to transfer a data to my output device. So this A0 is 1, so it is 1, here it is 1, this is 0, so this is 0 and this is 1. So output of AND gate 2 is 1. So it is act as load data signal. That means this data out register is enabled. So whatever the data that was placed at the input side, that will be transferred to output side. So that is the way how I transfer a data. And second case is if I read the status. In that case, everything is same. If I want to read a status, first thing is we change the logic level on this read/w write bar signal. This is changes to 1. If it is 1, so no doubt this signal is changes to 1. And output of this NOT gate becomes 0. So that output of this AND gate 2 0. Not it is 1. And coming to this, if I want to read a status, A0 signal is 0, no doubt. So it is not 1, it is 0. If it is 0, here it is 0. The output of NOT gate is 1. So this is now changes to 1, it is not 0. And but here it is not 1, it is 0. So now AND gate 1, all inputs are 1. So output is 1. If it is 1, read a status. Now it is act as a enable signal for this tri-state buffer. It will go and access SOut information with the help of D1. So like this output interface is helpful for us to transfer the data to a printer. I hope you understand how we are transfer the data to an output device, as well as how we are receiving a data from an input device with the help of input and output interfacing circuits. I hope you understand this concept. We will discuss in the next class an interface circuit which consists both the input function as well as output function. That we will discuss in next class. Thank you for patient listening.